In the diagram below, dv is equal to vx, which is equal to xe. vw is parallel to xy, which is parallel to ef. Prove that xz is equal to 3zy. Now, zy is a small section. Let's mark it in red. And xy lies next to it. So let's mark this in green. Both xz and zy make up the longer line xy. But the side DE, let's mark it in blue, is broken into 3 equal pieces: dv, vx, and xe. So from this, we can see that x is not the midpoint of side DE. So we cannot use the midpoint theorem. In questions like this, you will need to use smaller triangles within DEF to find relationships between xz and zy. So let's make the diagram black again. The best way to work with a question like this is to use what you've been given. Everything the question gives you is important. From the diagram, we can see that VW is parallel to xy. So let's start with triangle DXY. Let's make this triangle red. Now we can look at the information we've been given in triangle DXY. These two lines over here and over here show us that dv is equal to vx. This information has been given to us in the diagram, so we use given as our reason. The arrows over here and over here show us that VW is parallel to XY. And again, we can use given as our reason. Now we can see that V is the midpoint of DX and VW is parallel to XY. This means that W must be the midpoint of DY. So we can say DW is equal to WY. We also know that VW must be half the length of XY. So we can say VW is equal to half the length of XY. And as our reason, we use the midpoint theorem. Now we know that DW is the same length as WY. So on our diagram, let's put 2 small lines on DW and 2 small lines on WY to show that they are equal. Now we can make our diagram black again, and let's make some space. Let's make a note that VW is equal to half of XY. We can also see that XY is parallel to EF. Both lines lie in triangle VEF. So let's make this triangle red. Now let's look at the information given to us in triangle VEF. The line over here and over here shows us that Vx is equal to xe. And as our reason, we use given. The arrow over here and over here shows us that xz must be parallel to EF. And again, we can use given as our reason. Now we know that x is the midpoint of VE, and we know that xz is parallel to EF. This shows us that z must be the midpoint of VF. So we can say VZ is equal to ZF. We also know that XZ must be equal to half the length of the base of the triangle EF. And as our reason, we use the converse midpoint theorem. We now know that VZ is equal to ZF. So on our diagram, let's put 3 small blue lines on VZ and 3 small blue lines on ZF to show that they are equal in length. Let's make our diagram black again. Let's clear up our page. And also, let's make a note that XZ is equal to half of EF. Now we have an equation with XY and an equation with XZ. But let's see if we can find more information about ZY. ZY lies in triangle VWF. So let's make this triangle red. Now let's see what we know. So we can say in triangle VWF, we know that VZ is equal to ZF. Let's make a note. VZ is equal to ZF. We've just proved this. So as our reason, we say proven above. We also know that VW is parallel to ZY. So we can say VW is parallel to ZY because this has been given to us. From this, we can now see that Y is the midpoint of WF. So we can say WY is equal to YF. We can also see that ZY must be equal to half the length of VW because Z is the midpoint of VF and Y is the midpoint of WF. And as our reason, we say the converse midpoint theorem. We now know that WY is equal to YF. So on our diagram, let's mark YF with 2 blue small lines. Now we can make our diagram black again, clear up our page. We've just found that ZY is equal to half of VW. So let's make a note of this up here. We can now use these equations to prove that XZ is equal to 3ZY. We need to consider XZ and ZY. XZ and ZY. So let's find an equation that includes both of these terms. The whole line XY. So we can say XZ, this section over here, is equal to the whole line XY minus the smaller section over here, ZY. Now we have 3 equations that we found. And to work with these equations, we need 2 that contain a common line. VW appears in both of these equations. So let's move one equation down here and one over here. Now this part is a little bit tricky. VW appears in both of these equations, but it doesn't appear in this one, nor does it appear in the equation we need to prove. So the best place to start is to make VW the subject in one of our equations. So over here, to make VW the subject, let's multiply both sides by 2. Then we say 2ZY is equal to VW. Now we can substitute 2ZY into VW on this side. So we can say, instead of VW, we're going to have 2ZY is equal to 1 over 2 XY. We're almost done. We have ZY and ZY, but we need to prove that XZ is equal to 3ZY. So in this equation, we need to get rid of XY. So let's make it the subject, and we can multiply both sides by 2. 2ZY multiplied by 2 gives us 4zy, and we make this equal to xy. Now let's look at the equation at the top. We have xz, which we need to prove. We have zy, which we need to prove. Now we have xy, but we just found that xy is equal to 4zy. So let's substitute 4zy into our equation up here, and we can say xz is equal to, instead of xy, we're going to say 4zy minus zy. Now, zy and zy tells us we're working with like terms. So now we can simplify, and we say xz is equal to 4zy minus zy, which leaves us with 3zy. And we have now proved this equation.